Okay, this is the outline of chapter 31. So we will talk about the LC oscillation, which is the easiest second order circuit, which only consists of L and C. And then for the second part, which will be the damped oscillation in an RLC circuit. So after adding the R into the LC oscillation, then it will be a bit more complicated, but still manageable. And then next, we will talk about the phasor. The phasor maybe a difficult part of this chapter. I'm not sure. Yeah. So and then we talk about series RLC circuit, and then power in the AC circuit, and also the transformers. Yeah, transformers. Okay, so first is the LC circuit. So as you can see here, we have 8 figure here. So X phase in a single cycle of oscillation of a resistanceless LC circuit. The bar graphs by each figure shows the source magnetic and electrical energy. So in chapter 25 and chapter 30, you of course have learned for the capacitance. Yeah, as much as we store, we have some charges on the parallel plate. It will generate the E field pointing from the positive plate to the negative plate. And in that case, some energy will be stored in this E field. And for the inductor, as much as we have current going through this solenoid or the inductor, then it will generate the B field, mainly inside the inductor. But there may be some fringe B field outside. But yeah. But anyway, for this magnetic field, there will be some energy stored in the magnetic field. Okay, so this graph try to show the different status of the LC circuit and with the corresponding energy stored at different stages. So maybe let's start from this one for figure A. For figure A, we can see at this moment we don't have current. And all the charge are at the plate. And as much as there are no current, then there will be no magnetic field, which means that there are no energy storing at the inductor, and all the energy are stored at the E field. So you can see the full UE here. And for the next stage, it will feel like so as much as we have the charge here, the charge, as much as this is positive, this is negative, it will try to go through this inductor, and then they will try to neutralize. So in this case, the voltage across the capacitor will decrease. And as much as these charges try to going through this path to here, which means that there will be some current, right? So there will be some current going counterclockwise. And this current will generate B field by this inductor. So part of the electrical E field energy will be transformed to the B field energy. So the full energy will transfer to the magnetic energy here. So this process will go on until all the energy become all the UE become UB, and in that case, there will be no voltage difference between the parallel plate, and then in that case, the current will be maximized at this situation. So the magnetic field will be the strongest case. So we have all the UB, but no UE. So this will just keep on, yeah, and then this will keep on, and then the bottom plate become positive. For this stage, the bottom plate is negative, the top plate is positive. So up to here, we have positive bottom plate and negative charge top plate. And then, yeah, so part of the UB transform back to the UE. And then it keeps on, so this case is like this one, but the polarity of the plate is the other way around. We have a positive bottom plate and a negative top plate, and still all the UE, we have all the UE but no UB. So this is the other, yeah, so it's just like you just flip the circuit bottom, top to bottom. Yeah, and it keeps on and then going back to this situation. I don't try to go through it one by one because this is just like the symmetric of this one is like this one is like this one is like that. Yeah, so if you are familiar with the mechanical system, it is like if you have a string here, if you have a ball. So it is like you have you have no kinetic energy, but all the potential energy, and then it will swing to this case. So it is like this is A, this is B. So part of the potential energy changed to kinetic energy. And then for this situation, this is C, which is this one. So all the potential energy changed to kinetic energy, and then it will swing upward. So this is parts. This is figure D. Okay, so it's like this, and then for the part E, it is like here. So yeah, so all the energy transfer back to potential energy, but it is the opposite direction. It is just like all the charge going from the top plate to the bottom plate. So it's like this. So if you're going back, E, D, C, D, A. So it is so it's like E, F, G, H, E, F, G, H, and then going back to A. Something like this. So later in this chapter, I will show you that some of the mechanical system will have the same form of the ODE as the electrical circuit. Yeah, so this is the energy transfer. So it is like we have UE equals Q squared over 2C, or if you still remember, UE equals Q squared over 2C, or equals to 1/2 CV squared, something like this, if you still remember. And for UB, it is 1/2 LI squared. But it tried to explain all the things in a energy way. So it tried to write an ODE according to this energy. Yeah, so it tried to talk about the conservation of energy, something like that. And it tried to compare the LC oscillation and the block spring system, or usually I will call it the spring mass system. Spring mass system. I don't really sure how do you call it. So for this one, for the block spring system, it is like we have a spring. Yeah, we have a spring, and then according to the Hooke's law, you know that F equals minus kx. If you I suppose you should remember. And then for the kinetic energy, for the not the kinetic, for the potential energy for the spring, it should be like U spring should be 1/2 kx squared, like this. And for the block, the kinetic energy is 1/2 mv squared, which is what you should have known. And the first derivative of the displacement is the velocity. V equals dx dt. This is the velocity. Yeah. So compare with the LC oscillator, the capacitor is energy to the spring. So it is like so for the capacitor we have a Q equals CV. Q equals ZV, and then so it is like 1/2 1/CQ squared, which is actually this one. So you can just energy it by changing X to Q and then changing K to 1/C. And then for the next inductor is like the block. So for the magnetic energy, it is 1/2 Li squared. So that you can compare V to be the I. And as much as you know, I is dq dt. So that all the things will match each other. So M is the inductor. M is the inductor, V is the current, and V is the derivative of X, I is the derivative of Q. So all the things can have a good analogy. So in that case, for the spring mass system, you know that it should be oscillation. It should be some sort of oscillation. And the oscillation frequency is like 1 / square root of LC. So in the textbook, it mentioned the energy method. So just now in this page, we know that UE should be Q squared over 2C. UB is Li squared over 2, no matter which stages it is at. But for every moment, these two terms should be add up to be a constant because the energy is conserved. If we assume there are no losses here because we did not model the resistance here. Later in this chapter, we will also model the resistance, then there will be loss. Just like for the spring mass system, if you don't assume there are some friction force in between, or there is no losses in this system, then the spring mass system will oscillate forever, something like that. So now we assume the energy is conserved. So we have U equals UB plus UE, which is this term plus this term. So next, now so this is the total energy, and we assume the energy is conserved, or the conservation of energy, which means that du dt is 0. So we take the derivative of this equation should be equal to 0. So as much as we take the derivative of this one, L is a constant, so L is a factor out, and then I squared, we take the derivative will be 2I, So these two and these two will be cancelled. So we have I here, and then we still need the chain rule because it is like di squared dt is like di squared di times di dt, which is the chain rule. So di squared di is 2I 2i. So these 2 and these 2 cancel. So we have Li, and then di dt is actually this one. And for this one, similarly, take the derivative. We have 1 over 2c in the front, and then dq square dt is like dq square dq times dq dt. And we know that dq dt is, dq dt is I0, but we still rewrite dq dt here. And then here we have 2q. So 2 and 2 will be cancelled. So we have q over c here. So it turns out to be like this equation. So now we can see that, so far we don't see a second order ODE yet, but we have a di dt and dq dt here. And as much as we know I equals dq dt, so that we can just substitute this one into here to eliminate I, and then it turns out to be one unknown variable. One unknown variable. So So in this case, we can just have I to be dq dt, I to be dq dt, and then di dt is taking the derivative of I, which means it is d2q dt2, and then we still have L in the front. So we have L is this one, I is dq dt, di dt is d2q dt2, and then plus q over c times dq dt. Okay, like this. And of course dq dt is not 0, so this one and this one cancel. And then we divide L for the whole equation. So we divide L and divide L. So L and L cancel. So finally we have a d2q dt2, which is this term, and then so we have 1 over LC here, Q we write it at the back. So we can see this is a second order ODE without any input, without the g of t here, which is only a second order homogeneous ODE. Okay, so actually we can derive this equation using the energy method, and if you use the potential method, it is like we have C here, we have L here, and maybe we assume this is V, this is I, like this. Okay, so of course we have I equals C dV dt. Okay, so next, as much as I is going in this direction, so VL is like this, VL is like this. So we can see VL will be L di dt. So these two equations is really, really important when you try to solve the RLC circuit. So we can substitute this one into here. So it is like LC d2I dt2. Okay, so when you consider this loop, VL plus V should be 0, which means that LC d square I dt2 plus Yeah, so this is VL. So this is let me see. Yeah. No. Yes. Here it should be V because we substitute this one into here, so it should be LC D2V DT2. So this is V, and then so this is VL plus V to be 0 because you're going from this point, going up and then going up. So V plus VL should be 0, or maybe voltage drop going back to this point is 0. So it is like this. So you can have D2V dt2 plus 1 over LC V equals 0. Yeah, you may ask, we have a D2Q dt2 plus 1 over LCQ. So we have V for this one, we have Q for this one, but actually they will be the same. They will be the same because you can just for example, you can just multiply. You can first take the derivative. Take the derivative of this equation, then you will be D3 V dt3 plus 1 over LC, and then V dV dt, something like this. And then you can just multiply it by C. Multiply by C here. So this one is I. This one is I. Or maybe you can just take the derivative. Yeah, so this is I. So we have 1 over LCI like this. And then this one will be D2I dt2. Still, this is I, this is Q, so you can just take the derivative. Yeah, as much as you know Q equals, I equals dQ dt. I equals dQ dt. So you can just take the derivative of this equation. You can see you have a dQ3, d3Q dt3 plus 1 over LC dQ dt. So this is I, so this is LCI equals 0 plus D2I dt2. So these two are the same. So you can just take the derivative, multiply some constant, and then you'll see that they are actually equivalent to each other. So as much as this is a linear circuit, then no matter which variable you use, you can still write the same ODE. So actually you can really find this equation. And usually from a circuit analysis point of view, we seldom use Q as the variable. Usually we'll use V and I, to be honest. But this is a physics textbook. It tries to explain everything in a physics point of view, so it uses the concept of the charge. Yeah, I will not say it's incorrect, but yeah, we seldom use it. But actually they are equivalent. As much as you use Q or you use V or I, then you can actually, you still have D2V dt2 1 over LCV, and also you have a D2I dt2 plus 1 over LCI. So, yeah, so you can have the version for V, version for I, version for Q. Yeah. So it doesn't really matter which variable you use. Yeah, when we referring back to the spring mass system, it is like suppose we have a spring and the mass. So this is mass is small m, and yeah, and the coefficient, the spring coefficient is k. Yeah, so like this. Yeah, so actually we can just, yeah, maybe, so this is the reference point, and if it move to x to the right side, then there will be a force which is F equals minus kx. And as much as the force pointing to this way, then there will be acceleration. Then there will be acceleration for this mass, right? So referring back to the Newton's second law of motion, you know F equals ma, right? F equals ma, which is of course m times d2x dt2, the second derivative of the displacement with respect to time. And this is of course F equals minus kx. So in this case, we can just slightly rearrange the term. We have a d2x dt2 plus k over m times x equals 0. So this is still a second order ODE with respect to x rather than vi or something like vi or q. So comparing with maybe we can write a d2v dt2 plus 1 over ls, yeah, 1 over lc v, something like this. Yeah. So when you try to solve this, ODE, so this is a second order term, so you just write it as a s squared plus k over m to be 0. And in that case, s is a complex value because this is positive, which means that s squared is minus km, minus k over m. Minus k over m should be a negative value because k is positive, m is positive. So s has a complex conjugate root, which is plus or minus I times square root of k over m. So x should be like a cosine. Yeah, maybe you can just divide omega to be square root of k over m. So this is the oscillation frequency. So it is like omega t plus a b sine omega t. Yeah, but simply for actually we need the initial condition to determine A and B. But if we don't really care about the initial condition, usually you will just write it as x of t equals r times cosine omega t. Or generally you can write it like this is the amplitude, this is the phase. Because when you learn the trigonometry in high school, you know that even though A, B are arbitrary number, then you can just merge these two terms together so that it is like a cosine omega t cosine phi minus sine omega t sine phi. Then as much as cosine phi is something times, so you just so you just let r to be square root of a squared plus b squared. So you can just make a cosine phi to be a over square root of a squared plus b squared, and then sine phi to be minus b over square root of a squared plus b squared, something like this. Then you can rewrite it as this expression, which is equivalent. You have two independent variable a and b here. You have two independent variable r and phi here. But similarly, simply you can just make this 0, something like that, and this is just a simple harmonic motion. So similarly, if you try to find a solution to this one, or find a solution to this one, it is nothing but Q equals Q cosine omega t plus phi, which is actually the same form as this one. Yeah, it's just R times R cosine omega t plus phi. So here we have a small q of t is big Q, which is the amplitude times the cosine omega t plus phi. Yeah, and of course, if we try to calculate the current, going through the capacitor, which is nothing but taking the derivative of this expression. So taking the derivative of this expression is Q times omega, and then with a minus sign because the derivative of cosine is minus sign. So we have minus omega Q sine omega t plus phi, like this. So we'll say Q is the amplitude of the charge variation. Amplitude. Omega is the angular frequency. If you try to relate the angular frequency with the normal frequency, which is like omega equals 2 pi f, so this is so the unit of omega is radian per second. So this is radian per second. So for f, which is the normal frequency, the SI unit should be hertz, which is like 1 over second, or the second inverse. So the angular frequency. So omega is the angular frequency of the electromagnetic oscillation. And the phi is the initial phase. Suppose you let t equals 0, then this is a cosine phi. Yeah, so taking the first derivative thereafter. Yeah. Okay, so next we try to calculate the electrical energy and the magnetic energy. So as much as we know the expression of Q, then UE is nothing but Q squared over 2C. So it is like Q squared over 2C, capital Q squared over 2C times cosine square of omega t plus phi. So it's just to square this one and then plug in here. So nothing special for UE. And for UB it is 1/2 Li square. So we need to make use of this one. So we still take the square of this term. So minus square will be positive. And then we have omega square Q square. So we have omega square Q square. Yeah. And then let me see. So we should have, we should have Q squared over C in the front, but just let you know it is like 1/2 L I square is omega square Q square, and then still sine square omega t plus phi. Actually, we should know that this one should be the same as this one. Which means that omega square is like, because we know that omega is 1 over square root of LC. So omega square is 1 over LC. So this term should be 1/2 L times 1 over LC times Q squared. So L and L cancel. So we have Q squared over 2C, which is actually this one. So for UE and UB, they are two square of a sinusoidal. One is cosine square, one is sine square. And then the amplitude are the same, which is Q square over 2C. So in this case, you know that if we add them together, you know cosine square plus sine square should be 1, which means that UE plus UB should be Q square over 2C, which is a constant. If you just assume all the charge will not leak to somewhere else, then Q should be a constant. 2C won't change, so C is also a constant. So this one is a constant. So we do have the conservation of energy here. But yeah, for every moment, UE should be like this. Cosine square will be like this one. The blue line here, cosine square. And then UB is sine square, which is this green one. Yeah, you may be confused that why cosine square is still a sinusoidal, but actually, if you have learned the trigonometry, it is like cosine square of x is 1 plus 2 cosine of 2, sorry, not this way, should be like cosine of 2x over 2, something like this. Yeah. So for cosine square of x, cosine square of this term, it is like you still have a sinusoidal, but you shift it up. Cosine of something is from -1 to 1. So if you add this one by 1, then it will be between 0 and 2. 0 and 2. Which is still a sinusoidal, and then you divide it by 2, so that it is a sinusoidal from 0 to 1. So it's just like you shift up the sinusoidal, but the frequency becomes double. Yeah, so like this. And similarly, sine square of x is like 1 minus 1 minus cosine 2x over 2. So when you add them together, this term and this term cancel. So 1/2 plus 1/2 is 1. So cosine square x plus cosine sine square of x plus cosine square of x is 1. So we have the expression like this and the figure like this. Yeah, so here, so for this figure, it just assumes that phi is 0, but phi is not really important at this moment because we don't really have an initial condition. So you just take different reference time, then you can just shift this phase to 0. So we have 3 notes here. So first one is the maximum value of UE and UB are Q square over 2C. And any instant of the sum of UE and UB is actually this one. Because you have a cosine square plus sine square to be 1, a constant. So when UE is maximum, UB is 0, and conversely. So yeah, because they just add up to the 0, and the energy cannot be negative. So either one is maximized, and the other one is 0, and conversely. Okay, so maybe we stop here today.